I'll get back in a few minutes.
Okay, sir. Thank you very much, and good morning to everyone.
I've also made you the co-host, so we can start. We can do recording.
Okay, all right. Thank you very much. Good morning, everyone. I hope you're all doing well. It's been a long time we met, and since the last time, I believe some of you have completed school, at least those in level 400, and a very few of you have also moved a level up. So congratulations to those who just completed school, waiting for graduation. So we are going to continue from where we left off. And let me quickly share with you something so that we are guided by everything we are doing. So when we started off, these were some of the things we covered. And of course, this outline was shared with you. So it is still on the platform, actually. So we were able to cover up to, I think, the Python programming. Clearly, you could see that the things we wrote over here, there were like 3 major bullet points, but then indeed, we had to do a lot in there. Now, we're on this particular section where we'll be discussing data preparation and pre-processing for machine learning models. So typically, we are going to look at the exploratory data analysis and processes. We are going to look at the data generation for ML model, data preparation, finding class balance and imbalance, data visualization, feature importance and relevance plots, and data encoding. So clearly you can see that there's a lot. And we are hoping to use about 8 hours to complete this. So normally our sessions are in 2 hours, so you can do the math. And then from there, we'll go into the machine learning model development. Now, let me also share my screen here with you so that we have this. So with the core of everything we did, we looked at learning Python using this particular structure or method. So we had, like we were moving in that order. And I think at every step of the way, we're aggregating on the knowledge that we have. And yeah, so far so good. Now, let me just do this and clear this out over here. And let me see. Okay, let me just come in here. So we spoke about naming of variables, the various data types, and everything in between. Okay, we looked at the various Python collections, the list, the tuple, the dictionary sets. We also looked at functions. We looked at object-oriented programming that led us into learning about classes, objects, methods, and everything. We also spoke about modules and how we can import modules, how we can use modules and everything. Good. So today we are going to learn some few things, and we are going to build on our knowledge by learning some libraries, because those libraries are going to help us do the data pre-processing, the generation of data, and any other thing that we may want to do. Now, I'm just doing a little bit throwback so that we get some insights into some of the things that we are going to do today. So before we saw something like this, we could declare a variable first name, and first name is Kenneth. Then we also saw an instance where we'll declare a variable Ronnie, and then we can have full name. And what we ended up doing was doing something like this. So first name plus last name. And if I decide to print the full name and run this, we get full name being printed out over here. And clearly we saw this Kenneth Brony being joined together. We said this was something we refer to as concatenation. Good. So it is very good we know this. Now, one of the things probably I didn't tell you is that, please, can we all mute our microphones? I'm getting feedback here. So let's say I have a variable called data, and data is this star over here. Data is this star over here. Now, if I'm trying to, okay. Now, data is this star over here. And clearly we know that this is a string because it is declared in a single quotation mark, okay? Right. Now, if I'm to do something like this, I want to print data times 3. Now, this is a valid Python expression, okay? All I'm trying to say is pick whatever you have in data and multiply it 3 times. So it is going to see, or we are going to see star 3 times over here, as we can clearly see. Now, if I'm to do times 10, then the logic also works out over here. Picks this and multiply it 10 times, and that's what we eventually see over here. Now, based on this, we are going to learn some few things. Now, look at this. I'm going to have a list, okay? So in this list, I have 1, 2, 3. And I'm doing the data, which is this list, multiplied by 2. Now, ordinarily, this is a list, okay? It is not an array. Python, by default, does not have the array data type. And we are going to work with arrays a lot because through arrays, we are going to generate data and we are going to put things in data, in the array. And this is more or less, to Python, is more or less behaving like a string in a way. Because when I do this data times 2, it is actually going to replicate whatever thing I have there twice. So clearly, when I do this, we are getting 1, 2, 3, 1, 2, 3. It's almost like the star, which was a string. But then in this case, this is a list. But ordinarily or mathematically, if I do this, I am thinking about, okay, having an array, okay, and I'm multiplying this by 2. This is like a vector quantity, okay, and this 2 is a scalar quantity because it only has magnitude. And what I expect is doing some kind of a broadcast. So at the end of the day, based on the mathematics that we know, I was expecting, based on this expression, okay, I was expecting something like, okay, getting an array where 2 will multiply 1 to give me 2, comma, then this 2 also multiply 2 to give me 4, comma, then this 2 also multiply 3 to give me 6. That's based on the fundamental mathematical principle that we know. But then it is not working out right because of the fact that this is a list, and a list will behave this way. All right. Now, if I'm to do something like data 2 is equal to another list, and I do 4, 5, 6, okay, and I do data plus data 2. Clearly, the way this was behaving was, it was almost behaving like a string when we were doing the multiplication. And it is also going to behave like a string. So technically, what I'm doing over here is more or less like a concatenation of strings, except that these ones are lists. So it's just going to join or concatenate the members I have in data 1 and also the members I have in data 2. And definitely, that's exactly what we have. So we are getting 1, 2, 3, 4, 5, 6. But then, typically, what I was expecting in terms of its mathematical principle is to have something like a pairwise operation, okay, such that the first element will add up to the first element of both. So what I mean is the first element of the first list will sum up with the first element of the second list, okay? So in this particular instance, mathematically, I'm expecting 5, 7, and then a 9. And this is why we need some other libraries, and we are going to look at them as we go on. Good. So this is going to lead us to learning about some other libraries. And typically, we are going to learn about a library called NumPy. So this NumPy is something we call, it's numerical Python. Okay, that's like the full name, numerical Python. And it helps us with a lot of these data, especially when we are dealing with arrays. And we are later on going to learn about tensors and stuff like that. All right. So having said that, we are going to work with this library. So let me quickly come back here and show you something. And that has to do with some of the libraries we are going to work with today. So we are going to work with NumPy, and we are also going to use the Jupyter Notebook environment. So Jupyter Notebook. So NumPy and Jupyter Notebook. So I've said this many times, and this is a Jupyter Notebook environment. It is an environment where we can also write our code, okay? So what I'm going to do is I'm going to go into my command prompt, and that's where I am. Let me just clear everything up over here. And I'm going to do a pip install, and I'm going to type NumPy. So I expect you to do this probably maybe after this video has been recorded and you are watching out over again, you can do a pip install NumPy. Now I already have it installed, so definitely if there isn't a new version of NumPy, it is going to tell me that requirements already satisfied, else it will actually install the new version that is currently available. So this might take a while. Of course, you need internet connectivity. But then it is telling me that a new release of pip, whatever. Okay, so no problem. But then the point is, I already have NumPy over here. So if I'm to do a pip list, this is going to list all the libraries I have currently installed on my system. And it is quite a lot. Now, when you do a pip list, chances are you may not have the number of libraries I have over here. And some of them are not necessarily things I installed, but then they were libraries that depended on other libraries, so they all came along. But then they are listed in alphabetical order. So we are definitely going to go through it, and let's look for N. So the N starts from here, and then clearly you see that we have NumPy. And the version currently that I'm using is the 1.24.3. So this is a version of NumPy, and this is what we are going to use to work with arrays and do some wonderful computations with Python. So this is it. Now there's another library that I made mention of, which is the Jupyter Notebook. And with the Jupyter Notebook, let me see. So we are looking for Jupyter. Like I said, I already have it installed. So you are probably going to do a pip install Jupyter. And let me just show you, because I quickly want to go through this and make progress. So let me just come back here and okay. Okay, so if we are to go onto my YouTube channel, I have a video of the installation of Jupyter Notebook. It's a very simple process, and let me quickly run through that. I think that will be under this session. All right, and once again, everything we'll be covering with regards to NumPy, I also have videos on them, so definitely you can go back and do some references over here. But the point I want to make is this is the installation of Jupyter, and like I did indicate, it's just about 5 minutes, but then I'll just go in deep into a lot of things. All right, so all that we need to do is to, I think the command is, yeah, pip install Jupyter Notebook. So all that we need to come and type over here. And this, I want you to do it at least by end of today if you don't have Jupyter Notebook. So I want you to do pip install, then Jupyter Notebook this way. So you press enter, and in a matter of few seconds to maximum a minute, if you have very good internet connectivity, it is going to install. Currently, you can see that I have it installed. So most of the things being written out over here is requirements already satisfied. So it has some interdependencies with some libraries. So it will check everything. And if everything is okay, it will just tell you that everything is okay. So now we have Jupyter, and we are going to explore the interface a little bit, and we are going to write code in there. So everything we're writing in the VS Code environment, we can also write in the Jupyter Notebook environment. Okay. So that looks good. So what I'm going to do is I'm going to come onto my desktop and probably create a new folder. I don't know. Let me say, give it a name. And let me call this data analysis this way. So I'll open this folder. And once I come in here, I'll go into the address bar and I'll type in CMD and I'll press enter. So the point is I want to open my command prompt window, this window, okay, in this directory. And the directory I need is the data analysis, okay? Okay, so once again, in the video, I walk through that same process. So definitely that wouldn't be a problem. Let me just share the link in the chat so that everybody will have that checked. So now that we have opened this over here, I just want to activate the Jupyter Notebook environment. And the way I do so is I type in Jupyter Notebook, as simple as that, the name of the library, okay? So I'll press enter, and then this will start a server behind the scene, and it will open up this in my browser. So in a matter of seconds, I have this opened up, okay? And this environment is moving on what we are going to use most of the time to build our models and stuff like that. So inside of this environment, and this is similar to the Google Colab, which I'm going to show you very soon, okay? So this environment is what we have. So currently we have file. It's almost like any other thing or any other software you use. We have view, we have settings. So you can probably increase the font size, decrease the font size, and the other things, okay, depending on what you want, and then help and a few other things. But then what we want to do is inside of this files tab, okay, I'm going to click on this new. So when I click on new, it gives me some options over here. And what I want is I want a notebook. So when I click on notebook, it will open up a new notebook for me. Now, this new notebook is by default going to select a Python kernel, okay? So this one will happen, especially for those of you using Mac, because Mac by default has the Python 2 installed. And when we're starting, we installed Python 3. So probably we are going to see Python 3 and Python 2. But then for those of us using Windows, and probably this is the first time we install Python, we don't have to worry about anything over here. This one will be selected. Then we'll click on select. So now everything looks good. So now there's an interface we are going to do. Now, the way Jupyter Notebook environment works is like that. Every code we are going to write is going to be in cell blocks. So currently you can see that there's a cell block, okay? And you can type anything over here, right? Now, we can use these buttons showing up over here. And let me see if I can increase the font size a little bit. Let me see, edits, settings, okay. So nothing seems to be increasing. Okay, increase font size. Okay, no problem. So this is the terminal, okay, or this is a how do you call it, the cell. Now we can increase or we can add more cells by just clicking on this plus button, and definitely another cell has been included over here. So as many times as we click on it, we are going to have cells. Now, like we did, I can do name is equal to, and I'll say Kenneth. Now, when I want to run the cell, I just have to click on this run button over here, and now I get the option to either run the selected cell or run the cell below and other things, okay? Normally, you probably want to do run all cells, but then there's a shortcut over here. So I can do Shift Enter. When I do Shift Enter, clearly you can see that the cell has run, and we have this one showing up over here. So at the moment we run any cell, we are going to see some number, okay? If I run it for the second time, clearly we are seeing that we have 2 showing up over here. Now, if I want to display name, which is the variable storing the value Kenneth over here, I just have to type in name. And now when I do a Shift Enter once again, name is being printed out for me. However, if we're using this VS Code environment, after doing name is equal to, for instance, Kenneth, if I come and type in name over here and run this, it is not going to print out because I haven't used the print, okay? But in this case, it's cut down on, a lot of the typing, okay? But that's not to say we can actually say print and I'll type in name. When I do Shift Enter, it is still working out over here for me. So we can decide to do the printing, or we can start just putting out the variable and everything works. Okay, so this is how it works. Now, if you want to delete a cell, clearly when you highlight on the cell, you can just click on this to delete that cell. And maybe if you want to take the cell up, you can click on this. So now this one is up. If I want to bring it down, I click on the arrow buttons back and forth. Okay, so this is good. Now, you also find out that there are other reasons why, beyond the few things I'm showing you, why you are probably going to fall on the Jupyter Notebook environment. Because with Jupyter Notebook, it is a lot of things embedded in here. So remember, if I'm typing code, I type it over here in this particular interface. I type it over here, and my results are going to be displayed in the terminal. If I want to install, for instance, a library, I come inside of the terminal to install the library, okay? Or to type the pip install, whatever. Now, in the case of the Jupyter Notebook environment, for instance, I can do pip list over here, Shift Enter, and it's going to run and going to display all the libraries I have installed. So clearly, I don't have to have a separate space for typing code and a separate space for, the terminal. Everything is embedded. Okay, we can do everything over here. And there's more to this. And I'll also encourage you to watch another video that I have that's on, I don't know, I think this particular video where I discuss Markdown. I think for the level 200s and 300s, they have an idea of what Markdown is. And we are going to combine Markdown with our code just to make things look better. Okay, so we are going to use this environment moving on, but then I want to save this. So currently you can see it is untitled. Okay, so I want to give it a name, and I'm going to call this NumPy because we are going to learn NumPy today. So this is NumPy, and if I'm to go back to the folder, I have this NumPy showing up over here. Great. So I'm going to go back, and we are going to make progress from this point. So in order to work with NumPy, once again, let's go to my GitHub repo so that we have some kind of a starter template to guide us on what to do. So I think we all know this. So I'm just going to go through this quickly, and then I'll share the link with you exactly where you can get this. So we go through this and we are looking for NumPy. So I think it's a little bit down. So this is NumPy, and this is what we need. Okay. So I'm going to share this particular link with you so that you just type in this and then you get here. So when you click on the link, it will take you straight here. Straight to this place. And then you click on this code to download the zip file like we did before, okay? So this will download the zip file, and we are going to do the extraction. So let me just come back here, go to my downloads, and then do a double click of this and do the extraction. So This we've done over and over again. So this has been extracted, and let me just do a Control-C and bring it onto my desktop, okay, so that I can easily locate it. So this is what I have. And let me just change the name just to NumPy. Okay. So I'll open this, and then I'll open this once again. So these are some of the files I have in there. And then inside of the terminal, I'll come in here and type in CMD. I want to open the Jupyter Notebook environment in this particular directory. So once again, I'll type in Jupyter Notebook this way, and I'll press enter like I did before. And we are going to have, sorry, we are going to have this showing up. So pardon me if I'm moving too fast, but these are very simple things. And with the benefit of the video being recorded, you can always go back and go and watch some of the things we did. So over here, you can clearly see that I have a lot of files over here. Many of them are images, okay? So I have some images over here. And I have these two files. So I have numpy.ipynb. ipynb is a Jupyter notebook, okay? So when I click on this, I get to see this. And let me go back here. So clearly you can see that the last time I modified this file was 2 years ago. So the previous year's group who did this course, we ran through this process. So when I come in here, we have a number of things showing up over here. So these were some of the things we went through in this environment. Now, I purposely had this template.ipynb over here. So we are going to go through this template, and it's the same thing, except that this is where we have the code written, and this is where like you have a clean slate. You can practice on your own. All right. So we need to learn some few things. So this is NumPy for absolute beginners. So the big question is, what is NumPy? And let me just zoom in a little bit so that we all have a good view of everything we are doing. So NumPy stands for Numerical Python. It is a Python library used for array data computations and manipulations. So just as we couldn't just multiply list by a number, now with NumPy, we can actually do that. All right. So why do you have to learn NumPy and use it? So NumPy is faster than the traditional Python list. And we are going to see some few examples as we move along. Now, NumPy is one of the popular data science libraries. It makes working with numerical data easier and faster. And because we are dealing with data pre-processing and stuff like that, we are definitely going to follow NumPy. Now, NumPy is interoperable because it supports a wide variety of computer hardware and software. NumPy is open source library. We didn't pay anything for this, and it is being updated almost every now and then. It has a very large community for support and assistance. So if you run into any problem, you can just go on GitHub, and we are definitely going to find some help one way or the other. And it is very easy to learn. So we are going to see. So this is just an image I embedded in there. So the big question we need to ask is, what is an array? So an array is a data structure which consists of a collection of data types. Good. Now, we have some few images over here. So clearly you can see that we can have a 1D array. And the array, the concept of the array we have over here is nothing different from the ones we know in physics, okay? So where we have vector quantities and scalar quantities, okay? And definitely an array is going to be, please mute yourself, I'm getting feedback. The array is going to be a vector quantity, okay? Because it has both magnitude and direction. So clearly you can see that this, we are going to call this a row vector, okay? Because the data is the 3 and the 2 over here, and the direction is such that it is in a row, okay? The horizontal axis. If it was a column vector, then it's going to be in a vertical axis. So here we have the data, and the direction is the row we see over here. So this is just a 1D array. So we can have a 1D array that's a row vector like we have over here, and we can have one that's a column vector, which is just going to have, how do you call it? The numbers stacked on top of each other. Now, in the case of what we see over here, this is a 2D array. And a 2D array definitely is having directions in both rows and columns, okay? So over here, there's a horizontal direction, there's a row, and there's a vertical direction. So, and the data we have over here is the data we have in these cells. And now we can also have a 3D array. Now the 3D array is definitely going to have data being represented in 3 dimensions. So the first dimension is definitely going to be the row. The second dimension is going to be the column or the y-axis, okay? And the third dimension is going to be the z-axis or the z-axis. That's going to show the depth of data. And a lot of times, that's how data is, okay? Now, the interesting thing about NumPy and the way data is represented over here, which we are going to appreciate more, is when we start dealing with images, okay? Because images are nothing but arrays to the computer. Images are nothing but arrays to the computer. And we are going to see where the numbers are coming from and how things work. So just be patient and grab this fundamental concept very well. So already we have it installed. Other than that, we are going to do pip install NumPy. So we just skip this process. And now we need to import NumPy and work with NumPy. So just as the way we're importing libraries and modules late in the Python programming session, we can do import NumPy. So you can have it this way and everything is going to work. So now when I do this, normally with some of the books, you have this as import NumPy as NP. Now, what I have over here is, okay, this NP is now an alias that I'm using to represent NumPy. So anytime, I mean, NumPy is not too long, okay? But then there are some libraries in Python called Beautiful Soup, okay? There's a Beautiful Soup library. So imagine typing Beautiful Soup and you have to type Beautiful Soup all the time. It becomes problematic. So normally you see something or people say import Beautiful Soup as something like BS, okay? So that instead of typing Beautiful Soup all the time, I just have to type BS and I'm good to go. And that's the same concept we are using over here. So we are saying import NumPy as NP. Now, when I have it this way, I'll do a shift enter and then this will run. So currently you can see that this cell has run and everything is looking good. Now I'm going to uncomment what I have over here because I just want to print the version of NumPy that I have. And I'm saying np dot underscore underscore version underscore underscore. And that's simply because I don't have to be typing NumPy all the time. I just have to type np, which is an alias from the import of NumPy I have over here. So when I do a shift enter, there's a version of NumPy that I have. All right, so now let's move on to the business of creating arrays, manipulating data, and working with data. So I can do this. So let me create a variable x. And instead of just saying 1, 2, 3, which by default, this is going to be a list. Now I want to have a NumPy array. I want to have an array I can work with. So instead of doing 1, 2, 3 this way, I can do NP, which is the alias of the NumPy I have over here, dot. Remember the dot operator. Whenever you use the dot operator, I keep on saying this and I'll continue saying this. It's almost as if you want to go into it. So now when we go into it, what do we have? Unfortunately, if this was in the Jupyter, in the, how do you call it? The VS Code environment, okay? And if I'm to do import NumPy this way, we get to have IntelliSense helping us, okay? So now if I'm to do import NumPy as NP, so now if I'm to do X is equal to, and I do NP, which is NumPy dot, I have this IntelliSense showing me up all the things I have over here. And you can see that there are a number of libraries showing up. I mean, a number of functions and methods over here. So IntelliSense by default, we don't get it over here, okay? Because the moment I type in dots, nothing should. But then there's a trick we can use over here. When you do dots, you can click on the tab, okay? The tab key. So when you click on tab, it shows up everything you could have seen in the VS Code environment, okay? But then this is also good. Sometimes you don't have to be doing dots to see everything. You just have to also commit some of them in memory. So when I do np.array, there's an array method over there. And basically all that I'm trying to say is, okay, I want to fall on numpy np and create an array. So I bring in this parenthesis, because it is a method, I always have to bring this parenthesis. And the big question I need to ask myself, okay, what data do I want to have in that array? So I have to put this in a list, okay, or in this square bracket. And I'll say 1, 2, 3. So just as previously, what we did over here, where if I'm to do, let's say, y is equal to 1, 2, 3, same data, okay? But then because of the way things have been structured, their corresponding or their respective data types is completely different. And of course, we can use a type class to check. This is something we are quite used to. So now that I have this, I'll do a shift enter, and then this has been stored in memory. So I'll click on this and create some new cells over here so that I can explore the things I have over here. So I can simply do type X over here to check the data type of this X variable, which is storing some array, okay? So when I do this, I see that this is a type of data I have in there. So I have a numpy nd array, okay? So numpy nd array for X. Now, in the case of Y, we are definitely going to see that Y is going to be a simple list. So Y is still a list. If I'm to do a multiply by 2 over here, just going to duplicate the members over here. But then if I'm to do a multiply by 2 over here, and this is what I mean. If I'm to do X multiply by 2, clearly it is going to be 2 times 1, which is going to be 2. Then 2 times 2, which is going to be 4. Then 2 times 3, which is going to be 6. So currently, if I run this, that's exactly what I see over here. Okay, because this 2 is being broadcasted throughout each element. And that's what we want to have. However, if this was a y times 2, okay, a y times 2, this was just going to almost like the string, okay? So that is one of the reasons why we are using NumPy, because this one gives us the typical array that we know. All right, so now let's create a 1D array. Just as the images we saw over here, we can have a 1D array, a 2D array, a 3D array, a 4D array. In fact, with NumPy, we can create very higher dimensions of arrays. So with a 1D array, we are going to create a 2D array and a 3D array. But please pay attention because it is a very simple trick, okay? Now, let's come back and do x is equal to np.array. And once again, I'll type in 1, 2, 3. Now, what I have over here is a 1D array. So when I run this, once again, let me create some new cells over here. And now when I do x, which is the array dot ndim this way, all I'm trying to say is, okay, I want to check the dimensionality, okay, of, I mean, 1D means one dimensional. Is that okay? So when I do x.ndim, I want to check the dimensionality of this particular array that I have over here. So now when I run this, I see that this is 1. So clearly this is a 1D array. Good. Now we are going to use the same data we have over here to create other dimensionalities or the 2D array and the 3D array. And we are going to see a very simple trick as we move on. So over here, let me have y. And y is going to be equal to np.array. And once again, I'm going to open up a bracket over here. So this is the first bracket. And I'm going to open up another bracket over here. And I'm going to type in 1, 2, 3. So in terms of the data, it is still 1, 2, 3. But then the first one I had over here had just one opening bracket. This second one I have over here has 2 opening brackets and also 2 closing brackets. So now let's see. Around this, I don't seem to have any problem. Now let me create some cells beneath this and now do the same thing. So when I do y dot the dimensionality ndim, when I run this time around, it is telling me that this is a 2-dimensional array. Now let's try and replicate this with 3-dimensional array and see if this one works. So now let me do z is going to be equal to np.array. And now 1, 2, 3. So I have 3 opening brackets, okay? And I'll pass in the same data. So I'll do a shift enter to run this cell. And now let me just open this up a little bit. Now when I do z dot end die this way, and run this. This is a 3D array. So now the trick is, well, it doesn't really matter the data we are putting in there. However, to make things very simple, the number of opening brackets, which is definitely going to correspond to the number of closing brackets, is the first thing we should be looking out for if we are just to, eyeballing to see what kind of dimensionality of an array that we have. Okay, so that's just covering the basics of the dimensionality. But then there's more to this, because you don't just want to have the data we have is almost like a row array, but then we are just trying to wrap it up in some dimensionality. That's not what you want. Typically for a 2D array, you want to have our rows and columns and stuff like that. And we are going to see examples as we move along. So now let's look at a typical example. So now when I do, I come back to do x is equal to np.array. And this time around, I want to have rows and columns. Okay, I want to have rows and columns. So see what I'm going to do. I'm going to have this first square bracket and this square bracket. The moment you see two square brackets or two opening brackets, then this is a 2D array. Okay, so now I'm going to do 1, 2, 3. Then I'll come outside of this and bring in another bracket and do 4, 5, 6. So clearly, all that I'm trying to do is, okay, now this time around, yes, I want to have a 2D array because of the two opening brackets that I have over here. But I want to have rows and columns. So basically, this is going to be the first row, and this is going to be the second row. So now when I run this, everything looks good. And now when I print X, that's exactly what I see over here. So clearly, you can see that I have the first row showing up as 1, 2, 3, comma, and then the second row showing up as 4, 5, 6. Now the columns are automatically going to be sorted out for you, because this is going to be the first column, this is going to be the second column, this is going to be the third column. So these are the basic stuff. Now the point is, if I'm to check x.ndi, it is still telling me that this is a 2D array. Okay, so the catch is the first two opening brackets is what we are looking at for. Now, if I'm to bring in another bracket and also enclose this out over here, and then run this, then this now becomes a 3D array. But then the data still remains unchanged. And now the dimensionality has now moved from 2 to 3. But then there's more to this than just having dimensionalities changing, okay? But this is very good in order for us to understand certain things, because with some of the data that we'll be working with, we'll have to do some reshaping and resizing to make sure that the data fits in a particular structure. Okay, so this is very important we know. Now, let's look at another example, but then, very good. We cannot have a 1D array. Let's go back here. We cannot have a 1D array with rows and columns. Okay, if it is a 1D array, it's just going to be in one direction. So it is either going to be a row array or a column array. We cannot have a 1D array with rows and columns. So that's a very tricky one. So all I'm trying to say is, okay, this is something in rows and columns, because we are going to have this as the first row and this as the second row. So I cannot have this and this showing up over here. Okay, when I run this, it runs for a while and it tells me that, well, the field element must be 2 or 3 tuples, but got 4. It is even confusing as the more. But then the basic principle based on this image is, if it is a 1D array, just one dimensional, the moment we have rows and columns, we are making it 2-dimensional, because the rows will come in and the columns will come in. So I hope that makes sense, especially with this image that we see over here. So we cannot have this, because the moment we have this, this is going to represent the first row, and this is going to represent the second column. But then we only have one opening bracket, which is a 1D. So definitely one-dimensional cannot be rows and columns. It is either one-dimensional for a row or one-dimensional for only a column. It's quite exclusive over there. So now let's just bring this back, and now everything is going to work perfectly. All right, so now let's look at another important concept we have over here, which is checking the shape. So the shape is going to give us the number of elements for each dimension in the array. Remember, the dimension is a row and a column, okay? And I keep on saying that it is going to be row, which is the R okay, by the C. So look at this as RC, Roman Catholic, okay? That's very simple for you to appreciate this. So it is always going to count or going to represent things by the rows and columns. And we are going to check the shape, okay? So this one will return a tuple with each index having the number of corresponding elements. So clearly look at this particular one that we have over here. We know that, okay, there's a 2D array because we have two opening brackets over here and it has rows and columns. But then the number of elements we have in the rows is we have 1 row and 2 rows. Okay, so we have 2 rows over here. And how many columns do we have? We have 1 column, 2 column, and 3 columns. So we have a 2 by 3 matrix. Okay, if you are to look at it as a matrix. Good. So now if I'm to do x dot shape over here and run this, clearly that's what we see. So the first one we see is a row, counting the number of rows. And the second one we see is counting the number of columns. And that's why I'm saying that the shape, to check the shape, the number of elements for each dimension, the dimension is either going to be either the row or the column of the array. So it is the row by the column. And that's what we see over here. So now clearly you can see that we can also do a concatenation over here. And that's nothing different from what we used to learn or know. So what I'm going to do, sorry, is I'm going to have x is equal to np dot array, and I'm going to have, let's say, a 1D array. So I'm going to have 1, 2, 3. And let me have y is equal to np dot array, and I'm going to have, let's say, 9, 8, 7. So if I want to do a concatenation, now clearly if I do x plus y, if this was a list, it was just going to do the concatenation for me straight away. Okay, but then these are arrays, so it's going to do that pairwise addition. So typically, this is going to show up as 10, 10, 10. Okay, so now when I run this, I'm getting 10, 10, 10 because the first element of the first array will add up to the first element of the second array. The second element of the first array will add up to the second element of the second array, and in that order. Okay. Now, if you are doing this, then clearly we have to also be mindful of proportionality over here, because definitely 9 will add up to 1, 2 will add up to 8, and then what about 3? Okay, so clearly we get an error over here, and it says the operand could not broadcast together with shape. 3, okay, and then 2, nothing. So this is what we have over here. And clearly you could see that it's telling us of the shapes. Okay, so once again, let me just do this. If I'm to do x dot shape, remember this x is just a 1D array, so it's just in the row direction. So when I run this, it's telling me that 3, comma. Remember, whatever thing we have over here is the first one is going to be the row, and it gives nothing for the column because it has no column based on what we see over here. All right. So that's looking perfect for us. So now let me just come back and do the 9 over here. Now I want to do a concatenation. Okay. So now I can do np dot, I think this time around, concatenate. Very good. So when I do concatenate, I want to do a concatenation of x and y. And let me save it in a variable called z. So z is equal to np dot concatenate x and y. So when I run this, what do I have? It says only integer scalar array can be converted to scalar integer. What is happening? Only scalar arrays can be converted to scalar integer. Well, that's one of okay, so let's look at a matrix of higher dimension to actually see if this one will work. So let's say just by bringing the double brackets over here, we are making this a 2D array. So now let's see, z is going to be equal to np dot concatenate. Np dot concatenate, let me do x and y over here. And we are still having this, no problem. We are going to solve this. I think once we come in here, I think in this particular example, I used I used, okay, a different, all right, sure. So let's look at a more typical example where we have this 4, 5, 6. So this is like a 2 by 2 array, okay? And let's do a y is equal to np dot array, and then let's have let's say 6, 7, 8, and then let's have 9, 1, 1. Okay, so if I'm to do np dot concatenate, so np dot concatenate, and I pass in another bracket, so I'm passing in x and y, and then I need to specify an axis. So we are going to come back to this axis more often as we move along, because the way the rows and columns are structured, yes, they have axes, like I was trying to indicate earlier on. Like we have the x-axis, we have the y-axis, and we have the z-axis. Okay, so that's what we are trying to establish over here. So when I do this and run this, now this is what is happening. So the x-axis is okay, so now we have, let me put this in a variable called z so that it becomes very easy on the eye. Okay, so now originally we had 1, 2, 3. This was 1, 2, 3, okay, and then it's even more. Let me change the data over here so that it becomes very conspicuous for us to see. Okay, so now see, originally, if we print x out, okay, x is going to show what we have over here. I mean, from here to here, okay, forget about this, okay, x is going to show 1, 2, 3, 40, 50, 60. And then y is going to show 6, 7, 8, 9, 1, 1, okay, because this is a row, and this, like this is the first row, and this is the second row. So now, if we concatenate along axis 1, or we specify an axis of 1, all that we are trying to say is, okay, the zero axis so the one axis is going to concatenate along the row, okay, and the zero axis is going to be across the column. So if I'm to do a 0 this way and now run z, you can clearly see that this is almost stacked on top of each other. So still, it is still being maintained that this is x, which is 1, 2, 3, 40, 50, 60. And then this is our y, 6, 7, 8. Just a minute, I'm coming. Okay, so that's what we see over here. So we get the original x over here and the y stacked on top of each other. So clearly, the trick is the zero axis. The zero axis is going to be the column, okay, the column, and the one axis is going to be by the row. Okay, and we are going to see other examples. So clearly, you see that concatenating along the rows across the column. The feedback.
Please, if you are not muting because we are recording it, mute because.
All right. So let's move on. So now let's look at the stack function, okay? So the stack is also going to help us stack. And once again, to say stack is to mean we are just putting one matrix on top of each other or one array on top of each other. So originally we still have our x, when I print X, this is what we have. And then let me print out Y. If I do a printing of Y, this is what we have. So nothing has changed so far. But then let's look at how the stacking is done. And the stacking, we have a number of options. We have the H stack. So we have the H stack and then we have the V stack. And this should kind of communicate something. And we also have the D stack. So the H stack is stacking along the horizontal axis, which is going to be the row. And the vertical or the V stack is going to be stacking across the column, which is going to be the vertical axis. And then the D stack is going to be stacking in the depth, okay? So clearly you can see that, and that's why we have this over here. So we can go in depth, okay? And we are going to see this in proper manifestation when we are dealing with images, because the depth is going to show some different colorization and some few things. Okay. So let's see how we do this. So we have original X and Y showing up over here. And now let's do an A stack. So let me say Z is going to be equal to NP dot, and let me start off with a stack. So when I do a stack and I pass in my X and Y and run this. Okay, so let me do this way. So we need 2 double brackets over here for this to work. Okay, is the way the thing is. So now when I do a printing of Z, now this is stacking this by default in the vertical axis. But then this stack is a little bit different. You can see that this one is not the same as what we see over here when we're doing concatenation. Okay, now look at this concatenation very well, just by looking at this. Yes, of course, 1, 2, 3, 40, 50, 60. That's what we see over here. 1, 2, 3, 40, 50, 60. And then we have 6, 7, 8, then 9, 1, 1. We have 6, 7, 8, 9, 1, 1. But maybe, I mean, it's very obvious, but then let me just point it out. When we are stacking, it's like we put the whole thing on top of each other. But concatenation means we are joining. So clearly you can see that this was the whole thing. Look at the ending brackets over here. We had 2. So this is like stacking, like we just put one pile of metrics on top of each other. So it comes with its whole package. But the concatenation means we are just joining. So it just moved along and just joined along and just joined along. But then this time around, we picked a whole entity and stacked it up upon this whole entity. And this is very interesting because we can now do some of the things we used to do. So let's check the dimensionality we see over here. Clearly, without even telling you, we now see that now this is going to be a 3D array because we have 3 opening brackets over here. That's very obvious. So when I run this, we see that this is a 3D array. So now, if we are to check this one without even checking, okay, you agree with me that this is going to be a 2D array because we just have 2, how do you call it, opening brackets over here. So we get to see that, well, it is almost as if we are doing the same thing, but the technicalities in there are quite distinct. Okay, they are different from each other as with respect to the stacking and the how do you call it, the concatenation. Now let's also check the depth, and by checking the depth, we are going to check the shape. Okay, so when I do z.shape and run this, now we see something interesting over here. Just a minute. All right, sorry for the interaction. So now we get to see the shape over here. Now, clearly this shape we see over here is giving us an indication that, well, now this is not, in terms of its visual representation, okay, what we're dealing with the, how do you call it? The normal concatenation was giving us this. which was just a 2D array. Now we are getting something of this nature, which is a 3D array, and we are getting some depth. So this is what we see. We get to see that indeed we have this, looking at it as 2 rows, 2 columns, and it's having a depth of 3. It has 2 rows, 2 columns, and a depth of 3. Now, it is very difficult to explain it visually with this as we see over here, okay? Because if we are to look at it very well, it does not really make sense trying to explain it from this angle. But then the point is, whatever data that we have and whatever stacking that we have, we are later going to see that sometimes if it is in this shape, we can reshape it into other forms. That becomes very easy, especially when we are building our models. So that is something we need to keep in mind. So that's just with the normal stacking. Now we also have the H stack. So now let's look at the H stack. So typically X is looking like this, and our Z is also looking, sorry, our Y is looking at like this. So now let's see the H stacking, which is going to be on the horizontal row, okay? So when I do, Z is going to be equal to np.h stack. So H stack this way. And now I need to pass in whatever things I want to stack. So X and Y. So I run this, and now let me do a printing of my Z. When I do a printing of my Z, I get this stacked in the horizontal axis, okay? So originally, I had 1, 2, 3, and this is 1, 2, 3 over here. On the horizontal, stacked with 6, 7, 8. So this 6, 7, 8. So that's going to constitute the first row, and then the second row is going to continue like this. So clearly you can see that this is almost like the concatenation with the axis of, I believe, 1, okay? With the axis of 1 is going to do the same thing for us. And clearly, without even asking, we can take a quick guess and know that, okay, there's going to be a 2D array because of the two, how do you call it, opening brackets we have over here. And then if we are to do a z.shape, we are clearly seeing that, okay, we have 2 rows, that's the 2 we see over here, and we have 6 columns, and that's what we have over here. So these ones are very simple to see visually and also to understand. Now let's look at the vertical stacking. And once again, let me just create some cells beneath this. So originally, our X is still looking like this, and our Y is still looking like this. So now let's look at saving this in Z. So np.vstack. So V stacking, that's a vertical stacking of X and then Y. And let me just add in the other bracket, else we are going to run into that problem. So now when I do a printing of my Z, clearly this is what we're expecting. So originally, X was what we have over here. 1, 2, 3, 40, 50, 60. 1, 2, 3, 40, 50, 60. And it is being vertically stacked with our Y. And that's what we see over here. So over here, the point is, whatever that comes first is what is going to appear first. So now if I'm to do Y by X, what it means is I'm going to have 6, 7, 8 coming before the 1, 2, 3, okay, which is simply common sense. All right. Now, the D stacking is almost going to behave as the normal stack, okay, where we're getting some depth in there. Clearly, we got some depth of 3 over here. So now let's see how the D stacking looks like. So once again, let me just open this up. Our original X looks like this, and our original Y also looks like this. And then if I'm to do Z is equal to np.dstack, and I pass in X and then Y and run this, okay, we don't seem to have any problem. Now when I run this, this is looking like this, okay? And like I said, it is almost like the other one, except that, I mean, the normal stacking, okay? Except that the normal stacking was giving us, some 3 columns over here, okay, in terms of what we see stacked on top of this. Now, with a D stacking, let me see. So we have 1, 2, 3. Okay, we have 1, 2, 3. Then we have 6, 7, 8. So that's going to, and clearly you can see that there's a 3D, or the dimensionality is 3, and then it is being stacked upon the 40, 50, 60. Sorry, no, let me check the shape and the. So there's a 2 by 3 by 2. So 2 by 3 by a depth of 2. Okay, so sorry to say, but then the stackings are a little bit confusing, to be honest, because when we did the normal stacking, we had something which was very difficult to comprehend from the beginning. But then the whole point is when we are stacking, we are either stacking across the row or along the row or across the column. And we can do a stacking by depth or the normal stacking. And of course, we can do that comparison with the concatenation. But like I did indicate, it's good we know all these, okay? Because later we are going to see some reshaping and some few things. That's also going to make sense as we move along. Now let's look at other things that can also come up since we are dealing with matrices. So we can have a zero matrix. We can have a matrix of all ones. So a zero matrix is basically a matrix where all the elements or all the members are zeros, okay? And a good use case scenario is probably maybe you are working with some data and want to do some padding, okay? Want to pad some rows or some columns with zeros, or want to pad some places with ones and stuff like that. We can do this. So we can do, for instance, NP dots. If I'm to do zeros over here, and if I'm to pass in 4 and run this, that's what we see. So I'm getting an instance where I have 4 zeros. That's basically what I want over here. But then if I want to have, let's say, a 2 by 2 matrix where all the members are zeros, I just have to do it this way. So I just want to do np.zeros, and then inside of 2 brackets, I'll do a 2 by 2. So I want to have 2 rows, 2 columns, but then all the members are zeros. That's essentially what I see over here. So I have 2 rows, 2 columns, but then all the members are zeros. And clearly you can see that everything we see over here, the zeros we see over here are in floats, okay? They are in floats. I can come in here and do a comma and do a D type, basically specifying a data type, okay? So I'm enforcing this data type to be an int. So now when I run this, now clearly everything is now an int over here. So if I'm to do, let's say, a 4 by 4, I'm getting a 4 by 4 with everything explicitly being an int. If I don't bring this up, then everything is going to be a float. Now, it shouldn't always be a square matrix. It can be anything that we want. So this a 4 rows by 2 columns and stuff like that. Okay. Now the ones is also going to have the same format. So when I do np dot ones this way, and I pass in, let's say, a 5 by 5 matrix, I'm going to have everything in ones, but then it's going to be a float of ones, okay? And I can specify a data type of int over here, and everything is going to be an int. And like I said, we are going to come back to this later on. So this is just for you to see. Now we want to look at the indexing, okay? And we are going to look at the slicing. Now remember, when we're dealing with the arrays, okay, so for instance, if X was an array, if X was a list of, let's say, 1, 2, 3, 4, and I just do a printing, and let me just do this. If I just do a printing of X, oh, sorry, I didn't run this. So if I just do a printing of X, I get, sorry, I get 1, 2, 3, 4. But remember, we used to do some things like this, where we bring a square bracket, and if I want to select a specific element in here, we know that the elements over here are indexed, okay? They are indexed. So like all of them has a position. So 1 the first index position of the first element, which we see as 1 over, it has an index position of 0. 2 has 1, this is 3, and this is 2. Or we can say -1 if we decide to use negative index. So now, if I'm to do a 6 over here, it is definitely out of range, and that's what we saw. So it's a list index out of range. But then if I'm to do, for instance, a 0 over here, then specifically I'm getting 1. Now we saw an instance where we can do a starting index and an ending index. So if I'm to do this, the starting index is inclusive, the ending index is exclusive. So over here, the ending index is 3, which is going to correspond to the value 4. But because it is exclusive, I'm only going to have 1, 2, 3, okay? And this is something we spoke about several times. Now that same principle works over here with NumPy arrays, okay? So what I'm going to do is, and this is going to be an extensive one, but just bear with me. So we are going to have X is going to be equal to np.array, and let's do a 2 by 2 array. So I'm going to have 1, 2, 3, and I'm going to do a comma and 4, 5, 6. So we have this. I said 2 by 2, but I've done a 2 by 3, no problem. So let's do a printing of this, okay? Good. So you have 2 rows and 3 columns. Now, if I do X and do the slicing technique over here and bring in 0, this is what I'm saying. If I do X and bring in 0, by default, this is now going to give me the first row. Now over here too, the rows and the columns have an index position. So the first row is going to be an index position 0. The second row is going to be an index position 1, and it moves in that direction, okay? So if I do this, all I'm trying to say is I just want the first index position, which is 0. So that's going to be the first row, and that's exactly what we see over here, 1, 2, 3. If I'm to do an index position of 1, that's going to be the second row, or the last row in this case. If I'm to do an index position of -1, it's going to be this. If I'm to do an index position of 10, definitely this is out of range, okay? It says the index 10 is out of bounds for an ASCII 0 with size 2. Okay, so we can see this is working. Now, let's look at this. And let me rather make this a little bit interesting. So let's say I have another one, 7, 8, 9. Okay, so this is a 3 by 3. Okay, so now, once again, if I do X and pass in 0, I'm getting the first row. Now, what if I want to get, let's say, the first row, but I want to get just 1 and 2? Then there's going to be something that we need to do, okay? Or maybe I want to get the first row and the second row. If I want to get the first row and the second row, then of course, I want to start from 0 and end at maybe 2. Remember, based on the index position, this is 0, this is 1, and then this is 2. Now I'm putting 2 at the ending position because the ending index is exclusive. It's not going to be added. So over here with what we have, we're only going to see this, okay, 1, 2, 3, and then 4, 5, 6. And that's exactly what we see over here, 1, 2, 3, and 4, 5, 6. I could have left this blank because the moment I leave it blank, it is basically going to start from the beginning. And that's essentially what we have. Now, if I leave it this way, we are getting the whole thing. Now, the problem is, so far, everything we are doing is just dealing with the rows. Now, what about the columns? Okay. Now, in order to get the columns, then I have to introduce a comma. Now, when I do this, we are getting a problem over. It says there's an invalid syntax. And that's true. But then look at this. When I bring in a column over here and also another column over here and run this, I don't seem to have any problem. Now, this is where the magic is coming from. Now, this column is now going to, it's serving as a delimiter, okay, or a separator between the rows and the columns and where we want to specify. So now anything we have over here is going to be, anything we have over here is going to be on the row side, and anything we have over here is going to be on the column side. And the beginning of this is going to be the starting of the row, and what we have over here is going to be the ending of the row. And what we have over here is going to be the starting of the column, and what we have over here is going to be the ending of the column. So this comma over here is separating the rows and the columns. So now look at this. if I pass in, let's say 1 over here, all that I'm trying to say is, okay, I want to start printing from index position row 1. I haven't explicitly ended it up over here. So it's going to print everything from row 1 and everything from row 2 over here for me. So now when I run this, that's exactly what we have. We are starting from row 1 and we are also ending at this. Okay. Now the point is, okay, I want to print just 4 and 5. So we are still dealing with the rows. Okay. Now I want to print 4. So I'm starting with row 1 and I want to print 4. What is the column position of 4? That's the question we need to be asking ourselves. The column position of 4 is 0. So, okay, I want to start also printing from 0 over here. I want to end at 5. The column position of 5 is 1. But then because if I put 1 over here, the ending is exclusive. So I have to do a 2 over here. So now, let's look at this. The moment I see this comma over here, I know that, okay, we want to be very specific about the rows and columns. Whatever lies in front is the rows, and whatever lies behind is the column. Now, with this, I know that, okay, I'm printing everything starting from row 1 as far as the rows are concerned. But then when I come in here, I know that, okay, I want to print starting from column 1 and end at column 2. But then obviously because of the ending position is exclusive. So over here, we're going to have just a 4 and a 5. So now when I run this, okay, we are getting 4 and a 5 and also a 7 and an 8 because we didn't specify the ending of the row because the row is still printing. So to specify the ending of the row, then of course over here too, we need to say that, okay, we are ending at row 2. So we are only printing row 1 because we are starting at row 1 and ending at row 2. That means this one is exclusive. So this one will not be added. And then we are printing starting from column 0, which is the 4, and also ending at column 2, which probably was going to be the 6. But then because of the exclusivity of the ending index position, we are going to get 5 over here. And that's exactly what you see. Now, this can be a little bit tricky for the first time when we are working with this, okay? It takes time. But the point is, take it one step at a time, okay? In a sense that if you want to have this, just bring everything up over here, like I did from the beginning, okay? The most important thing is to have everything showing up over here this way. Then ask yourself, okay, so this time around, I just want to print out 6. I just want to see 6 over here. So the question I want to ask, okay, at what index position is 6? 6 is at the first index position because this is 0 and this is 1, okay? So I want to print starting from 1 because the starting index position is inclusive. And what do I want to end? I just want to end at 2. This one is exclusive. So now when I just do it this way, I haven't specified anything for the columns. So everything for the column, as far as this rule is concerned, is going to be printed. So now when I run this, I get this. But then I just want 6. So what is going to be my starting index position? I can simply do a -1. When I do a -1, it's going to count from behind, okay? So this is -1. And I don't bother about putting anything up over here. So I simply get my 6 showing up over here. Okay, so later on, I'm going to give you some few assignments just to try your hands on, but then take it one step at a time, okay? You don't have to clamp everything together. Okay, so now we have this. Now we are going to come to some arithmetic operations we can do with NumPy arrays and stuff like that, but we needed to get an understanding of what we see over here. Now let's look at creating a NumPy array from a list, and it's nothing different. Now we see X, or let's have data is equal to 1, 2, 3. Now I can see that X is going to be np.array, and I just pass in data over here. Okay, this is almost like how do you call it? A typecasting technically, okay, because we are calling this NumPy and we are putting this type over there to convert it into a NumPy array. So now when I do this and I'll do a printing of X, I have this now as a NumPy array. So we can do a typecasting of a typical list into a NumPy array, and we can do the other computations that we want. So now the point is the data type of the element. Okay, so now if I do X, as we know, X is this. If I'm to do a type of X, I know that there's a NumPy array, but then if I'm to do X and I do a slicing of 0, based on what we know, okay, this is going to be 1. So clearly I have 1 over here. And now if I'm to do a data type of X sliced 0, I'm getting this a NumPy int 32. Now, it doesn't change the nature of, sorry, it doesn't change the nature of the fact that this is an int, but because it is coming from a NumPy, NumPy is making sure that, well, it is tracking and even making sure that, okay, this of a 32-bit size of an int, okay? We can change the bit size to, let's say, 64 and other things. And that will happen if you are doing very large computations, and we know that, well, and this one will be more useful when we are dealing with floats, okay? Because for the int, we don't really have a problem. But then let's look at this. Let's say we have 1.9, sorry. Let me do this 1.9 over here. So we have, good. So now you can see that for the floats, I just changed this into a 1.9 just to make this a float, okay? So we have a 1.9 over here. We have a 1.9 over here. And now when we slice this, we are getting, but then when we check the data type, we are seeing a float of 64. And that's simply because with the int inside of the NumPy memory structure, okay, it is only reserving 32 bits for it. Now the int cannot misbehave in a way, okay, because integers, even though they are infinite range in terms of integers, okay, we can start from 1 and probably end at trillions or whatever, okay, but then with the float, we can start from between technically between 0 and 1 in terms of all the possible decimals in there. There are quite a lot. So over here you can see that inherently NumPy is kind of reserving more memory, okay, 64 bits for at least for floats. Just trying to tell you that, okay, well, for integers we can be a little bit flexible. 32 bits is okay, but then for floats between one range and the other can be a lot of different 0.000 something that we can never even imagine. All right, so now let's look at NumPys and how we can do additions and subtractions. And this, I mean, the basic things we know, but then we are seeing how we do them in NumPy. So let's say we have X is equal to NP dot array, and let's just do a 2x2 array. So I'm going to have 1, 2, and then I'll have a 4, 5 over here. And let me just create a number of cells under this. And let me also have Y, okay? So Y is going to be equal to NP dot, okay, let me just do a 1D array just for simplicity's sake, okay? But then the principles are the same. And let me do a 4, 5. Okay, so what are we getting over here? Okay, so now I can do an NP dot addition or add over here. Then what do I want to add? I want to add X and Y. It's as simple as that. So now let me save this in Z. And then if I'm to do a printing of Z, they're just going to do the element-wise addition. So the first element of the first array will be summed up with the first element of the second array. And the second element of the first array will sum up to the second element of the second array. And that's exactly what we see over here. So this is a very simple thing we can deduce out of. Now let's do the subtraction. And let me just do, let's say K is going to be equal to, and let me do NP dots, once again, subtract, okay? So I pass in X and Y. And then when I run this, it is basically going to do the subtraction for me. So it is going to do 1 minus 3 because it is going to be the first, sorry, it is going to be the first, the first element minus the second element. So 1 minus 4 is going to give us a negative 3, and 2 minus 5 is going to give us a negative, and that's exactly what you see over here. The multiplication is the same. So let me say M is going to be equal to NP dot. I think this one is multiply, yes. If I'm to do X and Y, and let me just print M over here, we are getting this. So clearly 1 times 4 is 4, and then 2 times 5 is going to give us a 10. And that's exactly what we see over here. The divide is basically going to be the same thing. So if I'm to do D is equal to NP dot array, NP dot divide. So NP dot divide, and I pass in X and Y and run this. We are definitely getting this because that division was done. Okay, now you can also find the square roots. So remember, earlier on, when we're dealing with square roots, we had to do import. We did something like this. Say from math, import SQRT in order to get the square roots for us to do whatever thing we want to do. We can also get square roots from NumPy. Okay. So let's say you want to find the square root of, let's say, a perfect square, let's say 81, okay? So I can say np dot sqrt, then 91. When I run this, so let perfect square 81, I get a 9.0, okay? Good. Now let me do something. So the 91 I had this, okay? Let's do a comparison with from math import SQRT. So the SQRT from math, we want to use that one and see how this one is going to work. So now let's say SQRT, and now let's pass in 91. Okay, we are getting the same value. I thought probably maybe we're going to get some truncation with the number of decimal places, okay? But then let me try something very funny. Okay, let me try this and see. It's basically giving us the same thing, okay? So it doesn't really matter. But then we can use SQRT from NumPy, and then over here we're using SQRT from the inbuilt math module, okay? So this one is inbuilt, this one is from NumPy. All right, now this is where it gets much interesting because with matrices, we'll be doing dot products and whatever multiplications that we want to do, okay? Good. So let me see the value of X. Okay, so X is looking good, and then Y is also looking good. So now let's see a dot product. And I think we know this dot product in matrices. So when I do NP dot, I think the dot product this way, and I pass in X and Y. When I run this, we get this. And please, I hope you all understand this because this is going to be 1 times 4 plus 2 times 5. Okay, so it's going to be 4 plus 10. And that's what we see over here, 14. All right. Now, with these ones, it becomes very simple for us to see. But then if we were to do X is equal to np.array, and this is where NumPy can come in very handy, okay? So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9. This a 3 by 3 matrix, a 3 by 3 matrix, okay? That's what we see over here. And let me just also do something for Y. So Y is going to be equal to np.array, and then let me just also make this okay. So we have this showing up over here. What is happening? It says invalid syntax. Okay, so this one. Okay, so now we have this and everything looks good. Now, if we are to do NP dots, the dot product of X and Y, this is where the magic is being done, okay? Because over here, it was going to be a lot of multiplications and stuff like that, but NumPy quickly will give it to us, and we don't seem to have any problem with this dot multiplication, okay? So now we can also look at the LCM, the GCD, and other things, okay? So let's say we have two numbers, we want to find the LCM of two numbers. So I can simply do NP dot LCM, as simple as this. And let's say the LCM of 2 and 5, okay? Clearly going to see that this is going to be 10. But then this is where it becomes a little bit interesting, because over here it says that the LCM did not loop through whatever. Okay, so because we're trying to find the LCM of floating point values, we're getting issues over here. But then you get a point. And the GCD, we can do NP dot GCD. And GCD of, let's say, 4 and 9, we get this over here. Now, this GCD is predominantly used in how do you call it, encryption and computer data security and stuff like that, okay? So let's say we are writing a script or a program that you want to calculate the GCD and use it for encryption purposes. You don't have to reinvent the wheel, okay? You just have to call NumPy, and NumPy is going to do the job for you. All right, so now let's quickly move on to the concluding part. We are almost done, okay? There are some few things just to cover, and we'll be done for NumPy. So now, clearly we saw the issue of broadcasting, okay? We saw some few examples. So for instance, if I have something like this, 1, 2, 3, and I do a multiplication of just a scalar quantity like 2, we are going to see this 2 multiplying 1 to give us a 2, this 2 multiplying 2 to give us a 4, and once again, this 2 multiplying 3 to give us a 6. So this is an example we've actually seen from previously. And now if we have a 4 by 3, so we have 4 rows and 3 columns, and then we add it up with just 1 this way, it is more or less going to stretch it up. So this 1, 2, 3 is going to add to the first row, the second row, the third row, and the fourth row. So over here, the result is going to be, if we add 1, 2, 3 to 0, 0, 0, the result is going to be 1, 2, 3. And then this 1, 2, 3 is going to add up to 10, 10, 10 to get 11, 12, 13, and it's going to move in that direction. So we are going to see this example very soon. But then there's always going to be a mismatch if we are, for instance, doing a 4 by 3, okay, and we are trying to add with a row column with 4 members. So once again, the logic is, okay, the first element will add up over here, the second element will add up to the second element over here, the fourth will add up, and then what becomes, the third will add up, and then what becomes of the fourth. So that's where the mismatch comes in. So we just have to bear in mind. So you can actually try this on your own with some examples based on the things we see over here. Now let's look at transposing matrices, because these are things that we do by hand. Whenever we are working with matrices, we want to find the inverse of a matrix and calculate eigenvalues, eigenvectors, determinants, and all those things that we know in linear algebra and also in how do you call it, in numerical methods. Okay, so let's say we have x is equal to numpy dot array, and let me just do a simple let's say 3 by 2 array or something like that. So let's say I have 3, 4, 7, 1, and then let's say 9, 0. And let me quickly print x over y. So this is what I want, okay? So these are the rows. So I have first row, second row, and then the third row. If I'm transposing, then it means that the rows will now become the columns. So it is going to be like flipping it, okay? All right. Now, there are 2 ways of doing this. We are going to see the normal Python way and then the NumPy way, okay? So now when I do x dot capital T actually, okay, x dot capital T, this is going to do a transpose of this matrix that I have over here. But then there's a, how do you call it? This is the Python way, okay? X dot T. So over here, this was the column. The column now became the row, okay, as you can see over here. And this second column now became the second row, as we can see over here. So this is a Python way of doing things. Now, if you want to use NumPy, then of course you have to do np dot. We want to go into NumPy. And what do you want to see? We want to get the transpose method over here. And it's as simple as this. So it is going to yield same results. But then, like I said, there's a Python way of doing things and there's a NumPy way of doing things. So it's very simple. It pretty much depends on what you want to do and how you want to go about it. But I believe the NumPy way, especially if you are dealing with very huge matrices, is always a good way to handle your transposing and other things. Now, we want to look at the inverse of a matrix. But before we look at the inverse, let's look at the determinant of this matrix. And if it is a 2x2 matrix, that one is very simple. We can simply do the calculation. But then if it is a matrix of higher dimensionality, then it becomes a whole lot of calculations. Okay. So now let's look at this. Let's say we have a matrix X is equal to np dot array. And let's just do a 2x2 matrix. So I have, let's say 1, 2, and then 4, 5. Okay. Okay. Is it the identity? No, I was looking at the determinant. Okay, I was thinking of the determinant. No problem. So we are going to look at the determinant very soon. So if it is the determinant, it is just going to be this multiplying this minus this times this. Okay, so the formula is very simple. If it is a 2x2 matrix, it's going to be 1 times 5 minus and then 4 times 2. And at the end of the day, we are going to get 5 minus 8. Okay, and for that reason, we are going to end up with a -3. So this is something we know. But then if it is a 3x3 matrix or a matrix of high dimensionality, then we have to be pivoting and doing some other things that becomes quite cumbersome. Okay, so let's check the determinants. So if I'm to do np dot, and once again, let's see determinants. Okay, so now we don't have determinant right away over here, okay, in NumPy. It is in there, but it's not in here right away. And that's simply because of the way it is structured, okay? So remember, when we're dealing with modules, we realize that some functions may fall under some particular folder and things like that. So over here, it is inside of the linear algebra. There's almost like a file in there, okay, or a folder in there. So when I do np.linalg, then everything I have under linear algebra will show up over here. So currently you see that I have determinant. This is a det. If I want to find eigenvalues and eigenvectors, this is what I have. Okay, I can have a lot of other things over here, and we can, I mean, there are lots of things. Okay, and we can do a number of things. So now we just want to see the determinant. Okay, so I just have to pass x over here, and now when I run this one is giving me something very granular. Okay, it's telling me it is I mean, it's a negative 2.9999996. I mean, when you run it up, you are getting your -3, but it tells you like the kind of work in there. Okay, so maybe for some reason we may want to, for instance, round this up. So remember, we employed a round method some time ago. Okay, so when I round this up, now we get a 3 over here, and I didn't pass any decimal point over it because I wanted to round up to the nearest whole number. So that's what we see over here. But then, once again, I think maybe the reason behind we getting this and not getting exactly how we have it here is, if it is a 3x3 matrix, then, I mean, you know, the computation is a little bit different, okay? A 4x4 matrix. So I think that's what probably has been used to optimize this process. But at the end of the day, you are going to get your results, and it depends on what you are doing. The good thing is you always check and make sure that everything is working perfectly. All right, so that's just going to be this. Now let's look at an identity matrix. And I think an identity matrix is something we already know. So if I'm to do x is equal to np dot identity, and over here, I'm going to say a 2 by, let me do a 3 by 3. Okay, let me just do a 3 over here. So an identity matrix is always going to be a square matrix. That's why I didn't have to do a 3 by 3. Is that okay? Good. And it is an identity because the main diagonal, okay, is always going to have 1, 1, 1, 1. And the upper triangular matrix and the lower triangular matrix, everything is going to be 0, 0. Okay. So back again, if you are doing the normal calculations we do by hand, the Jacobi and the rule elimination and all that, we can look at those formulas and see how we can combine. Okay, I just want an identity matrix of, let's say, a 3 by 3. So this is what I have to do, np.identity. Then I pass in 3 over there. Then I do whatever things I'm supposed to do, and everything is going to work. Now, I think for those in level 300, I believe, and of course, our final years who have completed with their exams, you definitely have had issues with eigenvalues and eigenvectors. And this is also going to be very relevant when we go into principal component analysis, PCA, okay? Because we are going to use eigenvalues and eigenvectors very much. So in order to get this eigenvalues and eigenvectors working properly, let me look at the inverse, the inverse of a matrix first before we come to eigenvalues and eigenvectors. So the inverse of a matrix, once again, the calculation is a little bit a lot, okay? So now let's have x is equal to np dot array. And let's do a 2 by 2, sorry, a 3 by 3 matrix. So I have, let's say, and this one, I'm hoping it works because some matrices, obviously, we cannot find their inverse, okay? But then, it depends on a number of factors. And then let me say 4, 6, 1. Okay, let me see if this one works. So when I run this, okay, this is a 3 by 3 matrix. And the question is find the inverse of this matrix. Okay, so NumPy is going to help us. So I can do np dot the linear. Once again, this one is also in the linear algebra. Then I do dot inverse. So this is dot inv. So this is going to give us the inverse of this matrix. So now when I put in this and run this, okay, this one we get this. Now you can try this by hand, but then clearly you could see that the numbers you are getting, negative 0.075, even if you are to do this by calculator, you are definitely going to miss some steps, like something wrong may happen, okay? So once again, NumPy is helping us find the inverse of a matrix. And you can imagine if this was a 4 by 4 matrix, then the problem becomes a little bit complicated because we are calculating the determinant. And you can imagine, I know for those of you who have taken the linear algebra class and the numerical methods, you definitely know what I'm talking about. But then once again, let's try this with NumPy. So let's say we have 10 over here. This is going to give us a 4 by 4 matrix, 90, and then 1. And let me also give out the last row. So this is 3, 0, 1, 1. So yes, we have a 4 by 4 matrix, 4 rows, 4 columns, okay? And then if you have to find the inverse, this one is also giving it to us. Very simple and very quick. So we didn't have to do the calculation. But once again, if you have time, you can do this manual calculation yourself and come and compare with this answer. But then there's something interesting happening over here. And is this fact that, okay, the numbers that we see over here, we see, for instance, a negative 5.621, blah, blah, blah. Then E negative or minus 0.2. So remember when we were dealing with the floats and stuff like that, we said, okay, for floats, this is what we use to represent scientific notations, okay? So this, as you see over here, is times 10 to the power negative 2. So definitely the how do you call it? The decimal point is about 2 points. So this has, if you are to actually look at this number very well, it's probably going to be negative 0.0056, but then because of the scientific notation, this is what we see over here. And you see that the other ones are also showing up as this. Okay. Now to the eigenvalues and eigenvectors. And once again, let's calculate the eigenvalues and eigenvectors of this. Okay. And trust me, if this was in, any of the numerical exams, for students to calculate this, they would rather look for other questions if things were optional, okay? But then NumPy is going to help us. So we can do np dot array, np dot, this one is also in the linear algebra packaging there, okay? Then over here, we are looking out for the EIG, okay? That's going to give us the eigenvalues and eigenvectors. So we pass in the matrix over here, which is this 4x4 matrix, okay? If you have to do this, probably the smartest person in this class will probably take about not less than 20 minutes, I believe, to be very specific and to make sure that everything is correct, okay? Now, when I quickly do this and run this, NumPy is giving it to us. But then this looks a little bit disorganized because we want eigenvalues and eigenvectors. So actually what we see over here is we have two arrays, okay? The first array is what we see over here. This is the eigenvalues. And the second array we see over here is the eigenvectors. And we see that, and this is what I'm saying, this one is a very tricky and very difficult one because over here we see plus a 0.j and other things. And this is basically some complex numbers. So this one is not a very simple thing to solve. Okay. So now what we can do is we can decompose this into, let's say, e values, comma, e underscore vectors, okay, is equal to this. So that all the eigenvalues will be saved in the e values and all the eigenvectors will be saved in the e vectors. So now when I run this, everything looks good. And now if I'm to do a printing of the e values, I get my eigenvalues. And if I'm to do the e vectors, I get my eigenvectors. And like I said, this is, a very difficult one to solve, okay? Because almost everything is in complex numbers because we are trying to find the root of negative numbers and you have to now apply complex numbers and all that. So I think that 20 minutes is even an underestimation, probably hours, okay, to actually come by this correct answer. So now let's look at this. Now we also want to find the determinant of a square. Okay, I think I've already covered that. But then we already know that for determinant, it's always going to be of a square matrix. Okay, we cannot find a determinant of a 3x4 matrix. It is not square. Okay, a square matrix is a matrix that has equal, the dimensionality in terms of rows and columns are the same. All right, we can also use NumPy to solve linear algebra or system of equation, okay? So this particular question, which I think last year we wrote using Cramer's rule to solve, okay, good. We can also use how do you call it? The NumPy to solve this. So over here, we have this system of equations. So x plus 2y is equal to 6, this equation 1. And then 3x plus 4y is equal to 16, this equation 2. So now when we decompose this into a matrix, we get this, okay? So this is going to be like the main matrix. These are going to be our variables, and this is going to be the right-hand side. So now let's solve this and see how this one will turn out. So we want the main matrix. So I'm going to call this main matrix. And it's going to be an np.array. Based on what we see over here, we know that, okay, the first row is going to be 1, 2, okay? But then this is going to be a 2x2 matrix. So the dimensionality is 2. So I need to have 2 brackets over here, then 1, 2. Then I put in a comma. Then the second element I have is what? 3, 4. Then I run this. So now let me just do a printing of this and see if it is exactly what I see over here. So clearly I see 1, 2, and 3, 4. That's exactly what I see over here. Now the right-hand side, okay? The right-hand side, okay? So let me call this right-hand side, and it's going to be np.array. And this is just going to be, I think, yes, just this matrix, okay? So we have a 6 and a 16. So I run this, and then if I'm to do this, I get this. And this is what I need to solve my linear algebra or system of equations. So I can do NP dot, once again, this one is inside of the lin alg, and then I think this one is solve. So basically I'm saying, okay, NP dot linear algebra, I want to solve this system of equation. So once again, I'm going into it once again to get a particular method. And what do I need? I need two things over here. So over here, I need the main matrix. So let me just copy this, the main matrix. And then I also need the right-hand side of whatever thing I need over here. So now when I run this and I get this, so I get 4 and 1. It's as simple as this. So now we can see that x is equal to 4 and then y is equal to 1. So now let's plug in 4 and 1 over here. If I plug in 4, 1 times 2 is going to give me 2. So there's 4 plus 2 is giving me a 6. Okay, so that looks good. Now if I plug in 4 over here, 4 times 3, I'm getting a 12 plus this is 1. This is going to give me a 4. So I'm getting a 16 over here. So we can actually confirm that indeed this solution is correct, accurate. Okay, so we get to see the power of NumPy. Anything that deals with matrices of any sort, there's something NumPy can give us to do that computation. And NumPy is optimized. It is very quick. Okay, all right, so now we can also do this truth table thing that we saw earlier on. Okay, but then this one we are going to use that bitwise operation. Okay, and these ones are not predominantly relevant to whatever thing we'll be doing over here. So maybe you can just look at this in the video. This is also covered. Okay, but then our time is up. That's why I want to conclude over here. But then the file that we are going to download is going to have almost everything I spoke about. Okay, with regards to the examples and a lot of other ones you are going to see over here. And this one also show examples over here. So, okay, so for instance, we have A is equal to 0 and then B is equal to 0, like this one, A is equal to 0, B is equal to 0. So when I do an NP.bitwise OR operation, so A or B, it is giving me a 0 because for the OR operation, it is just one of them needs to be 1 for it to be 1. But then in most cases, all of them are 0, so it is going to be 0. Then over here, I'm doing a bitwise AND operation. So over here, when I run this, it is still going to give me a 0 because it is still going to be 0 and 0. Okay. Now we can also convert from let's say binary base 10 to binary. Okay, so this is the number 19. When I do np.binary underscore rep r and pass in the number, it is going to give me strictly the binary representation. Okay, let me just show that over here. Let's say I have number is equal to 19. Okay, if I do np dot once again binary this, okay, and passing number this way, this is what I get. Okay, but then what we see over here is I add in a padding bit. So I want it to be in 10 bits. Okay, so it's will definitely add this padding bit for us. So now when I do a width of let's say 10, that's what we see. So we are getting this padding bits, but then at the end of the day, the binary nature of this number is what you see over here, 1001. All right. So probably we can end here because these are the fundamentals of NumPy. Okay. We have to understand that the natural list is not going to give us the opportunity to be doing multiplication and other interesting things we want to do with numbers. But with NumPy, we get the opportunity to do some data manipulation. So back to the structure we have over here. Yes, we are going to deal with the exploratory analysis, hopefully next week when we deal with pandas, okay? But they work hand in hand. So you have to have some knowledge of NumPy so that when we are working with pandas and we get some data structure and want to convert into a NumPy array because we want to do some multiplication, you definitely fall on the knowledge you have with NumPy. Good. And once we are done with that, we look at some few other things. The rest of the things we have over here is pretty much going to come along as we move on. All right, please, any questions?
If you have any question, please just raise your hand so that we call you. Okay. So it appears everybody is cool with what we have done so far. Either they are cool or they are being stressed. Somebody has raised their hand. Yes, please.
Sherry, if you can proceed with your question.
Yes, please, thank you very much for a nice presentation. Please, we're talking about us getting the file. I wanted to ask, where are we going to get it from?
What, the file?
Yes, please.
The audio. Is it the audio or data file? This presentation?
Yes, please.
Okay.
Not this. Not
which one?
The Jupyter.
Okay. So I think maybe you joined late, but then don't worry. Link. Everything is recorded.
Get on the link. Just
yes.
Go on the link. Okay.
So this is the so let me share that once again.
Okay.
So please just share it on the link on the platform so that
okay on the platform, sure,
they can get it.
Yes, please. Thank you very much.
You are welcome.
Okay. So are there any questions? Yeah. So if there are, I think this is a jammed thing. So heavily packed. So, but this is just the beginning. So we will close and then give you some time to digest what has been done. And then our next meeting on Tuesday, then we start with the actual process. Let me summarize what we have just done today, 2 minutes. First is that we have introduced you to NumPy, the library that helps us to do fast numeric computation. In machine learning, we have different data formats that can be when we are done with that, then we go to the textual data. So the textual data will take us through the natural language processing. So for now, we are focusing on just the numeric. When we are done with it, then we go to that. So the numeric, this is the beginning because all the data you see will be in numeric form for whatever, whether you are using a model for your GPA or you are using a model for predicting weather conditions, or you are using a model to classify health conditions, whether somebody has asthma or not, or somebody has malaria or not, whichever. These are all numeric data that we will use. So on that note, if there are no further questions, we'll close today. If you have any comment, you can share it on the platform. Thank you very much to everybody. So we are closed now.
Thank you very much, Dr. Mills.
Okay.